Alright, so in our last class, we talked about functional groups. So let's review that really quickly before we introduce some practice together in identifying functional groups in complex molecules. And moving on to formal charges after that. So when we talked about functional groups, what do we mean by that? What is a functional group? This was one of your questions on the homework. What is a functional group?
Collection of atoms or bonds that have the predictable countable behavior.
Okay, so that was our word-for-word definition. So we have some atoms or types of bonds, as we saw when we wrote down all our different functional groups, that have a pattern that they follow in terms of reactions. Because remember, that's what chemistry, and especially organic chemistry, is all about. What kind of reactions can happen? So yeah, we can identify certain structures, bonds, atoms, the way they're linked together, and we can know how they're going to behave. And by behaving, we're saying that they're doing something. So that's where the function and functional group comes from. They're actually performing a task. So what were our three, or at least how I divided them up, what were our three subdivisions for our functional groups? Our three big categories. Yes, sir.
Carbon with multiple bonds, carbon bonded to an electronegative atom / atoms, and C, carbonyl.
Carbonyl.
No.
Carbonyl, not Chernobyl, carbonyl. Alright, so our first heading there was carbon with multiple bonds. So primarily, we were talking about alkenes, alkynes, and our ringed forms that have multiple bonds within them as well. Now the multiple bonds were important because, well, first of all, what is a bond between two atoms? What is exactly doing the bonding?
Two electrons.
Electrons, right. So let's take one of these multiple bonded carbons stuck together, or whatever atoms they are. Because they have multiple bonds, we have multiple extra electrons in there. And we know that electrons do things for us in chemistry. They do the bonding, or they do the reacting. That's the heart of what chemistry is. And being that there are extra of them, that means that they're capable of doing something. Which again harkens back to what it means to be a functional component, or a functional group. Alright, so our second one was a carbon bonded to an electronegative atom. So we had examples of this, like carbon bonded to nitrogen, oxygen, very electronegative atoms there. But as a great thing to always review, can someone tell me what an electronegative atom is? What does that mean? Yes, Amber.
It has a desire for electrons.
Perfect, perfect. So being electronegative means you have a desire to gain more electrons. And that desire wanes as we go across the periodic table. If we were to look at the periodic table, which side would we find the most electronegative elements?
The right.
Yeah, the right side. So on the periodic table, if we're looking at fluorine, chlorine, all the guys right next to the noble gases, they are very electronegative. And that's because if they gain that electron or two that they need, they'll become just like the noble gases, octet happy, they'll be unreactive, and that's how things like to be in nature. So if we have a bond between an electronegative atom and another one that's not so electronegative, we'll find that the electrons will be drawn toward the electronegative side there. And when you have that disparity of electrons and how they're distributed within a molecule, again, you're talking about electrons being maybe concentrated somewhere. There's a capability to undergo a reaction there, because those electrons might be available to move, slide around in one way or another. Alright, so our last class was our carbonyl. So we were talking about the special relationship between carbon and oxygen, when we had carbon double bonded to an oxygen. And we had a whole variety of different schemes of this that we saw. So again, we're running across a case where there's a double bond happening, so there's more electrons. And furthermore, carbon and oxygen, well, oxygen is very electronegative. We see that in water. That's why water is a polar molecule. So, not only do we have extra electrons in our double bond, we have an electronegative atom in there. Carbonyls tend to be very reactive, and they have a wide variety of uses. Alright, so that's a good summation of our last class. And you had practice on your homework, and I'm sure you all did very well on that, because most of you turned that assignment right away. So it must have been pretty easy. Either that or I just did an excellent job teaching it. Or it could be both. Alright, so let's try looking at a few real molecules that, in fact, I know you're familiar with all of these. And with even the last one, you probably have used or ingested all of these. But the last one, as I said, might not be as common, but if you've had some sort of major procedure, maybe you've had it. So let's draw the first one up here. Consult my notes here myself so I don't mislabel anything here. Alright, so here's our first molecule. Does anybody want to take a guess, a stab at what this might be? I don't expect you to know it perfectly, but let's just throw something out there.
Octane?
Octane?
Yeah.
That's...
No.
Is it oxycontin?
Oxycontin? No.
Morphine.
No. No. This is something that you usually take for pain. Sometimes you'll take it if you have like a heart condition.
Aspirin.
Aspirin. Yeah. Very good.
I said Vicodin.
You take a baby aspirin, prevents you from getting a heart attack now.
Aspirin. Now, aspirin has a scientific name that we would probably use if we were organic chemists more often. And it is...
What is acetaminophen then?
Let me make sure I spelled that right. Yes, I did. Okay. So you said what is acetaminophen? That's just another molecule. We can talk about it at some point if you want to. But do you mean what it is? That's Tylenol. Yeah. Acetaminophen is Tylenol. Alright, so the real name here is acetylsalicylic acid. And that's quite a mouthful. Hence you see why pharmaceutical companies, drug companies come up with these more user-friendly names like aspirin. How would you like to have to say all the time, I'm going to go take some acetylsalicylic acid? That's a mouthful. Try to say that.
It's a tongue twister.
Alright, so let's identify some functional groups here. This is like the real practice now. Consult your notes. Tell me what our functional groups are here. What do we have? Ooh.
Carbon double bond oxygen.
Okay, so we see that here and here.
Aromatic.
So those are our classes of our carbonyls, right? We have like some specific names.
Aromatic.
And yeah, right here. So we have an aromatic. This is our nice ring. What's the other name for an aromatic? Yeah, arene, arene. And just to point this out, we see this E-N-E ending here because it's referring to these double bonds. Remember, anything with an ene ending is in with carbon double bonded to another carbon. So that's where the ene part comes from. Alright, so we have an aromatic group here. What else? There's one here that's like the name of an old woman. An ester. Yeah. Where's our ester?
It's the right one.
This one? Yes. So that's our ester. That's our hopefully I'm not offending anyone here. That's our old woman molecule there. Our ester. What about this last one?
I'm gonna say carbo.
Yes, you got it. You got it. Alright, so up top here, we have our carboxylic acid. I am just going to abbreviate this as CA. Because carboxylic acid is a long one to write. So there you go. There's aspirin. Honestly, 3 functional groups, it's not that many. But imagine if you were a pharmacist and someone's taking aspirin and they come in and say, can I take this other drug or this other medicine? This molecule alone right here has 3 different functional groups that could interact with this new substance and could potentially produce, by reactions, a harmful byproduct that could be toxic to you, or it could just nullify the effectiveness of this. So you have these 3 functional groups in that case, and you don't know what the other thing is. So there could be a ton of reactions that you would have to be aware of. That's why being a pharmacist is difficult. And it takes a long while, and you have to go to school for many years because you have to know a lot of these reactions. Alright, let's do our next one. I'm going to take my paper here with me so I don't have to keep consulting it. This one is quite complex. Alright, here we go. So there's lots going on here. But once again, we'll play the game. Take a guess. What do you think it is?
Morphine.
Morphine? No.
Yeah.
Not morphine.
Adderall.
Not Adderall.
Is it a drug?
Yes. Here's my hint.
Like heroin.
Maybe when you were little and you got sick,
Yeah.
you would go to the doctor and you would get prescribed this medicine that would be like this tasty pink liquid.
What kind of stuff were you eating?
The Bismarck.
Oh, yeah.
Oh, I'm trying to remember.
It starts with an A and it ends in cillin.
A ceiling.
Amoxicillin, yeah.
What kind of purple stuff are you guys drinking?
It's pink.
I'm colorblind at heart.
So, amoxicillin. I remember when I was little and I would get sick, I would always be so excited when I had caught something that required amoxicillin. I just looked forward to taking it. It was so delicious. And I remember even as I got older, you know, and they switch over to the pill form after a while, as you get older. I remember I would have my mom ask the doctor if I could be prescribed still the liquid one, because I wanted it. Like, please, I want the liquid. Because it was so good. Amoxicillin.
It's like bubble gum.
It just, I haven't had it in years. I just remember it's good.
I have a question.
Yeah.
In the structure, is the S connected to, is it making a pentagon?
Yeah, this is just a corner.
Okay, I drew.
Instead of a carbon here, it's a sulfur.
Okay.
Alright, does anybody know what amoxicillin is, say, like a form of or a derivative of?
Penicillin.
Penicillin, right. And does anybody know the story of penicillin?
Paris Hilton.
Isn't there one with the dog Bolt? Is that
The dog?
yeah? With like Alaska. I don't know.
I'm not sure. That might be a different medicine.
Okay.
What?
Wait, in Bolt, is that what they used? Like, yeah. Was that penicillin or what was it? Okay, I can't
We'll have to
remember.
look that up. That sounds like a curious story.
Yeah, it's a true story.
Alright, so no one knows penicillin? Penicillin? Alright, this is the, I don't know if the 100% historically accurate version, but some scientists were working with mold, and they found that bacteria wouldn't grow next to it. So they found out that something in the mold must have some sort of antibacterial, antibiotic property. And it turns out that penicillin, that's where penicillin was first discovered. And now we have a couple different forms of it, amoxicillin being one of them.
Originally, we were ingesting mold.
A component that came out of the mold.
Right.
Yeah, that's where it was discovered. It's an interesting story, yeah. Alright, so parts of amoxicillin. This is a complex one. You just have to, it's like a big meal. You have to work your way across, little bites at a time.
Ah, take it all in.
We have our aromatic.
Okay, so our ring here, right?
Yeah.
Alright, so we have our aromatic. Our arene again. Again, the E and the amine there for our double bonds. What else?
Bless you.
A ketone? No ketone, but you're close. An amide. Right, now where's our amide at here? We might have more than one.
Yeah. Do we have 3 of them?
I count 2.
2. Okay. It's just like single nitrogen. Is that right?
Right here?
Yeah. And then the one to the right of it too.
Right down here?
Yeah.
Yes. Alright, so these are both our amides. Alright, now we have something that's kind of close to amide. In fact, it's one letter off.
Amine.
Amine. Right, and where's that at? Yeah, right here. So there we have our amine.
On the end on the right at the bottom is the carboxylic.
Yeah, very good. So I'll just call this Ca for carboxylic acid once again. And just to point out a trend here, if you remember from when we were talking about acids and bases, whenever you had this OH present, that typically designated some variety of acid in certain cases. Like think about, remember H2O, when it can be considered an acid, sometimes it could also be a base, but when it was considered an acid, it would have this whole deal that it did with the hydroxyl group, the OH.
There's a sulfide too.
A sulfide. I'm going to say you're talking about the part involving sulfur. Right here. So we have our sulfides. Very, very good.
Oh yeah.
Alright, did we have one more thing. The OH? Yes. Okay. So this isn't. Well, I guess, yes, we did specifically call that. It wasn't alcohol. We specifically named it, I'm sorry. This is also known as a hydroxyl group. Now here's something new that we didn't talk about in our last class. Whenever you have an aromatic and an alcohol joined together, that has a special name. So this whole component here, the aromatic and the alcohol, is called phenol. And And remember, in sort of our naming trend pattern, whenever we end in OL, we're talking about some type of alcohol, like ethanol, methanol, pentanol. But phenol here, the phene part here is referring to the aromatic. You got it. Look at that huge molecule of amoxicillin. We know all the parts. Now imagine again you're that pharmacist and someone's taking amoxicillin and they want to take something else with it. Look at all the functional groups that are in here and all the potential things that could happen. That's pretty impressive that your pharmacist knows that stuff. Does anybody in here have pharmacy aspirations? I thought there might have been one. Yeah. How are you feeling about being a pharmacist?
A lot.
Well, you're starting early. So you're starting to learn this stuff and you have many, many years to master it. So it's not too bad. Alright, let's do one more practice of these before we talk about formal charges. And after we do that brief introduction to formal charges, you can do your practice. Probably take a break before we start that. Alright, so let me draw this one. Alright, I think I got all of it there. Alright, one thing of note before we play our guessing game again. Again, remember our solid triangles here designate that something's like coming out of the plane of the board. So this nitrogen is being stretched out of the board, and this bond to this carbon right here is also being pulled out of the board, and they both come together back down to form this carbon over here. Alright, so take a guess of the name.
Give us a hint. Is it a drug?
Yes, morphine. Morphine, you're right.
I hate you, Brian. I hate you. That's not even cool.
Morphine.
I hate you. I hate you.
I was really hoping you would just yell out morphine again, but the one time. Yep, it's morphine. Now, morphine, if you don't know, it's something that they used to use more commonly in the past until they found out its addictive properties that it has. It's a very strong painkiller, and if you have some major surgeries or something, you'll probably get some morphine at some point or another, but just in small controlled doses. Some people are allergic to it, and if your dose is just a little bit off, you'll probably get sick and throw up from it. So often, if you're in the hospital, they might try to guess like your weight, your mass, your body mass, and they'll try to calculate the right amount of morphine to give you, and it's generally not exact the first time, so you might get sick or it might not be strong enough. And then after that, they'll adjust it and they'll get it right.
Can you taste it? You know how like if it's going through an IV, I hear people can like taste.
That could be. I've never had morphine, so that could.
Ever had
be.
surgery?
What's that?
Have you ever had surgery, like major surgery? Ever breaking bones?
Remember he broke his wrist?
Yeah, I broke my hand and wrist, but I didn't do anything about it. Now it has a broken bone in there. Oh, and I broke my finger too. Apparently I don't care about broken bones, which isn't necessarily a good thing. Alright, let's identify our
Don't
person.
do what Mr. Schnorr does when you break a bone.
Alright, so you're identifying this group here as a phenol. And our subcomponents here are our aromatic chlorine and our alcohol. And together they form our phenol. Very nice. Well, do we have another alcohol on here?
Yeah, down the bottom.
Alright, so we have another alcohol.
Amine.
What's that?
An amine.
An am with an N? Yes. So that is right here, right?
Mm-hmm.
Yes. Those are am or amine. Not the D, it's the N one in there.
I thought it was two.
Alright, we have two more. Yes, ether. Right there. And the last one we haven't had yet, but it's actually kind of an easy one, but you might just overlook it because of its
Is it
simplicity.
alkene?
You got it. Wonderful.
Oh, it's right there.
So we have our alkene right here.
It's
Very good. We're all pros. Professional pharmacists in here.
What's the career I was looking at?
Does anybody need more time? Just one, a couple more seconds?
Question. What does meth look like?
Methamphetamine?
Yep.
Breaking Bad.
Is it like?
I would have to look that one up.
Or is it like really, really, really complex, or
It's
like in all
so good.
seriousness?
I'd guess complex.
I can pull up a picture on my computer really quickly if you're curious.
Not like
Actually, I'll do
the
it.
actual drug. I'm talking about the
Thank you,
show.
Walter White.
Yeah, it's an amphetamine and it probably has a methyl group somewhere in there. That's the meth part. Alright, we're all good with this? Good? Good? Alright, one more small section, then we'll take our break and you can start to practice.
Bailey. Bailey. Say no to drugs.
Alright, so formal charge. Obviously, you can tell by the name that it is always wearing a tuxedo, it's buying corsages for its prom date, take it to the prom.
Yeah.
Promise.
But
Really?
Boo.
Alright, formal charge is actually an equation. So here are our components of the equation. It's our number,
A hash sign.
of valence electrons minus, or we're taking away from it, the actual number of electrons around an atom. That's formal charge. So let's do an example here. Let's take CH4. And for clarity, I'm going to add the dots here on the end, just so we know that there are two electrons here. Each dot represents one of the electrons. And it'll help us to identify or calculate the formal charge more accurately. First of all, what is CH4? What is CH4? What is our one carbon organic?
Helium.
Okay, helium's an element that is not carbon, but good try.
Methane.
Methane, yeah. Okay, so this is methane. Methane. Alright, so to calculate formal charge, I'm going to isolate our carbon here, and we're going to just examine our carbon. Alright, so formal charge, I'm going to abbreviate it as FC. Okay, what is our number of valence electrons around carbon? 4. Subtract from it the actual number of electrons around carbon here. We have 1, 2, 3, 4. So the formal charge around this molecule is 0. 0. It doesn't have a charge associated with the outside. And we can do this for hydrogen too. Because we know that hydrogen has 1 valence electron, and it has 1 electron right next to it. So again, no formal charge on the hydrogens either. So this is an electrically neutral molecule. Kind of boring though, not that exciting. Let's just do CH3. And we'll pretend that through some event, the extra pair of electrons that would make carbon stable have been ripped off. It's been ionized. So, what would our formal charge be here? What should I write down? I'll draw our dots here for clarity once again.
So it's 1. Formal charge is 1.
So you said 1?
Yeah.
Okay, so how did you do that?
Well, I know there are 4 valence electrons on carbon, and then there are 3 shown. So.
Right. So carbon always has 4 valence electrons. That's why we have that number 4 in both of these cases. And this time though around carbon we have 3. So 4 minus 3 is 1. So this carbon has a positive charge around it. Nice positive here. Now whenever we have carbon with a positive charge, we give it a special name. We call it a carbocation. Because remember, our cation part here tells us that we have a positive charge, and the carbo is carbon just without an N. It's a carbocation. Let's do one last one, and then we can take our break. Let's do the same scenario. Only this time, we'll add our 2 electrons on there. Isolate our carbon here again. What would our formal charge be in this molecule around carbon? What's that? -2. Well, -1. So carbon, 4 valence electrons minus 1, 2, 3, 4, 5.
Would it be called a carboanion?
Ah, good. But there's just one small change. Because O and A and the carbo anion would be together, we just drop the O. So it just becomes a carbanion. Anion again is the negative. Alright, so one last thing I have to tell you, or else you're not going to have any idea what this question is asking on your assignment. Alright, there's a term called steric number. Steric numbers. Now let's see here. Should I have... Yep. I want to make sure I'm not confusing it all here. And I should have done this with our positive version. So, steric number is equal to the number of electrons around our atom. So in this case we have 3 per carbon. And we subtract from that the number of the pairs of valence electrons. In this case, we don't have any valence electrons. In this one we did, and this one we did not. So 3 minus 0 is 3. Now what steric number is it tells you, based on this value, based on this little calculation, what the general or likely geometry of the molecule might be. It's going to tell you how it'll be shaped. Remember when we had the models out, and we would kind of twist and bend them around, at least I would twist and bend them around, and we'd find those different conformations? The steric number helps us to guess what the conformation might be. Alright, so another additional thing. Being that this isn't CH4, this has a new hybridization that we haven't talked about yet. It's not sp3 hybridized, it's sp2 hybridized. Alright, so if we take our sp2 hybridized form here, and we say that this is a flat plane, our carbon and our hydrogens would be in the same plane. Now because we don't have this extra bond here, we have a free p orbital that is perpendicular or orthogonal to our plane here. That's going up and down. It's unbonded, so it's open. This is why it's not sp3 hybrid, it's sp2, because we have this open p orbital that's not doing anything with another s. It's just sp2. And we call this trigonal planar. Trigonal planar. The plane part comes from, or the planar part
What the
comes
heck
from
just
the fact that
happened?
this is a flat plane. And the trigonal comes from like triangle, because you could actually draw like a triangle around the structure. So triangle plane, or trigonal planar. Anybody have any questions? Alright, let's stop there. We'll take our break and we can practice our assignment.